Okay, let's look at our test review for rational functions. In question number 1, here we have a rational function given to us. We need to sketch its graph. So we're going to go through the RADI process to help us do this. R stands for roots. And remember to find the roots. We need to take our numerator and set it equal to 0. And when I do that, I get x equals 2. And so that means that my graph is going to have a root right here at x equals 2. The A stands for asymptotes. These are the vertical asymptotes. And to find the vertical asymptotes, we're going to take the denominator and set it equal to 0. And if I do that, I get x equals 3 and x equals -1. So those are going to be the two asymptotes for my graph, at 3 and at -1. Okay, next up is the T, which stands for tangency and togetherness. And to determine this, we're looking for squared factors in the factored form of our equation. And so I notice that I do have a squared factor in the numerator. And so that means I'm going to have tangency at x equals 2, because that's the root of that factor that's squared. But neither of the factors in the denominator are squared. So that means we have no togetherness. And it's important to write that down and remember because it's going to help us sketch our graph later. E stands for end behavior, another way to talk about horizontal asymptotes. And for that, I just want to know if my graph has a limit as x is going to infinity. Now, in order to best tell this, I need to have the highest degree term for the numerator and the denominator, which means I need to consider what my function would be if I multiplied it out, since it is given to us in factored form. Well, if I squared x minus 2, my first term would be x squared. That's going to be the highest powered term in the numerator. In the denominator, if I multiply x minus 3 times x plus 1, I also get x squared. And so considering both of those, if I plugged in infinity for x, if x gets really, really big, my numerator and my denominator are both getting bigger at the same rate. And so in that case, they're going to basically cancel out, and I'm going to be left with 1. And so y equals 1 is my horizontal asymptote, the limit for my end behavior. Alright, and finally, the Y-intercept. We're going to plug in zeros for the x's. Zero minus 3 over 0 plus 1. So I've plugged in a 0 for all the x's. In my numerator, I would be left with -2 squared, which would be 4. And in the denominator, I've got -3 times 1, which would be -3. So my y-intercept is -4/3. Whoops, not there. -4/3 is bigger than -1, or more negative than -1. So I'm going to graph that right there. Okay, so now we're ready to sketch our graph. I have these 2 points, my x and y-intercept, and so I know that those 2 points have to be connected. I know they've got to be connected, and I also know that at the y-intercept, my graph has to cross the y-intercept, and so it's going to keep going down towards the asymptote. So the question here is, what happens at x equals 2? Does my graph cross and go up to the other asymptote, or does it go back down? Well, remember at our t, tangency at x equals 2, right here, that tells me that my graph is not crossing, but it's going to turn around and go down this way. So now I need to draw 2 more pieces on the outsides of these asymptotes here. And I remember back from my T that we have no togetherness. And so what that means is if this part of the graph is going down, then on the other side of that asymptote, we have to be going up. And same thing is true on the other side of x equals 3. On the left side, the graph is going down, so on the right side, the graph has to be going up. All right, next question. In this question, we've got another rational function, but this time it's not in factored form, and so the first thing that we need to do is factor it. My numerator doesn't factor, but in the denominator, let's see, I'm going to get x and 2 and 2, both negative. So x plus 1 over x minus 2 times x minus 2, or we could write that as x minus 2 squared. Alright, so let's go through the steps of radii. Roots, we're going to take our numerator and set it equal to 0. And so for root, we get x equals negative 1. So right here, there's our root. Asymptotes, we're going to take the denominator, x minus 2 squared, and set it equal to 0. And so I get x equals 2 for the asymptote, only one asymptote. I'm sorry if you hear that coughing in the background. That's my old sweet dog, and he's a little sick. Alright, next up is T. T is for togetherness and tangency. So we're looking for squared factors in the numerator or the denominator. And in this case, I don't have a squared factor in my numerator. So I'm going to write no tangency, but I do have a squared factor in the denominator. So this graph does have togetherness. Whoops. I don't know what I was spelling with an X. Togetherness at x equals 2. Alright, in behavior, we're going to think about the limit as x goes to infinity. And I'm just considering the highest powered term in the numerator and the denominator. So in this case, if x is getting bigger and bigger, going to infinity, my denominator is going to get bigger much faster than my numerator. That means that if my denominator is getting really big, my fraction is getting very small and approaching 0. So that means that y equals 0 is our horizontal asymptote. And I do have a root here. We are going to cross the horizontal asymptote, but remember that's okay. The horizontal asymptote is only an asymptote out at the ends of the graph, out at infinity. Alright, and finally, y-intercept. If I substitute in zeros for all my x's, and you could do it in the original function like I'm doing, or in the factored form, either one. And either way, I get 1/4 for a y-intercept. So my y-intercept is going to be right here. Okay, so now we're ready to draw a graph. I've got these 2 points, the x and y-intercept, and so I know those are going to be connected. At the y-intercept, the graph has to cross. We always cross the y-intercept. And so it's going to cross, and it's going to go up towards that asymptote. Now at the x-intercept at -1, remember from our t, we have no tangency, and that means the graph is not going to turn around. It is going to cross there at -1. But we also know that the graph has to approach that horizontal asymptote. And so what's going to happen is it's going to curve back up like this and approach the asymptote. Alright, we need to draw one more piece on the other side of the asymptote. Remember from our t that we do have togetherness. And so that means that if this part of the graph right here is going up, the other side will be going up as well. And so that is our graph. Now in questions 3 and 4, we're given a graph and we're asked to write its equation. And the way that we're going to do that is we're still going to go through the radii process. Let's start with R, which stands for roots. And I can see here that I have a root at x equals 2. Whoops, there we go, x equals 2. And so what that means for my equation is that in my numerator, I'm going to have the factor x minus 2. It also seems that my graph has, the next thing up would be the asymptotes. And I've got a vertical asymptote here at 3, at x equals 3. And so that means in my denominator, I'm going to have the factor x minus 3. All right, next up in our radii process is the t. So we're looking for tangency or togetherness. Tangency happens at the root, so I'm looking right here, and I can see that the graph is crossing the x-axis. So we do not have tangency. For togetherness, I'm looking at my asymptotes, and I notice that, or looking at the graph on either side of the asymptote, I notice this piece of the graph is going down, and this piece of the graph is going up. They are not coming together, so I also have no togetherness. So we don't need to square either of these factors. Now usually by the time you get through RAT, you should have a good equation for your graph. We can check it though. Let's consider in behavior. It looks from my graph like my horizontal asymptote is right here at y equals 1. That seems to be the horizontal asymptote. And if I consider the limit as x goes to infinity of the function that I have written already, I'm just looking at x over x, both of those would be approaching infinity at the same rate, and so it would indeed equal 1. And finally, the y-intercept. If I plug in zeros to the equation that I have, I get negative 2 over negative 3, or positive 2/3, and that seems to be a reasonable number for where this graph is crossing the y-intercept. So I think we've got a good equation here, x minus 2 over x minus 3. Question number 4, we're going to do the same thing. Let's go through the radii process. For roots, this time it looks like the only root I have is at x equals 0. And so for my equation, that means in the numerator, I'm just going to have an x. Asymptote, looks like I've got an asymptote. I'm going to say it's at 2. It's a little bit hard to tell. And if you had said the asymptote was at 3, I probably wouldn't have counted it wrong because you can't exactly tell from this graph. But I think it's at 2. And so x equals 2 is our asymptote, which means in my denominator, I should have the factor x minus 2. All right, now we're on the t. Tangency or togetherness. For tangency, I'm looking at my root right here, and I can see that the graph does cross the axis. So no tangency. Togetherness, however, if I look up here, I can see that on either side of the asymptote, the graph, both sides of the graph are going up. They're coming together at the asymptote. So I do have togetherness at x equals 2. And so what that means is in my equation, I need to square the factor on the bottom. Now again, once we get here, we should have a good equation for our graph, but we can double check it by checking the end behavior. On this graph, it looks like my horizontal asymptote is at y equals 0. And so if I take the limit as x goes to infinity of the equation that I've come up with, my numerator is just x, And in the denominator, if I squared x minus 2, my first term would be x squared. And so in this case, if x is going to infinity, the denominator is getting bigger much faster than the numerator. And if my denominator is getting really big, my fraction is getting really small, and in fact it is approaching 0. So those match. That seems to be correct. And finally, the y-intercept. If I put 0 in for the x's, I get 0 over 0 minus 2 squared, which is 0, and that is indeed my y-intercept. And so that checks out as well. So I think we have a good equation here, x over x minus 2 squared. The remainder of the test review is going to be in part 2.